Hello, this is the final project for machine learning presented by Fangyuan Liu&Yuan Tian from NYU Shanghai, and the topic is predicting the success of Kickstarter projects using RNN and SVM. Kickstarter, which was launched in 2009, is one of the largest crowdfunding platforms in the world, having launched over 390,000 projects and having received pledges worth more than $3.6 billion as of April 2018. On this platform, project creators choose a deadline and a minimum funding goal. If the goal is not met by the deadline, no funds are collected. According to statistics released by Kickstarter, the success rate of fully funding a project on the crowdfunding website was only 36.02%. In July 2012, Wharton professor Ethan Malik and Shin P conducted research into what contributes to a project's success or failure on Kickstarter. They looked into more than 57,000 projects. Here are some of the key findings. For an average 10,000 project, a 30-day project has 35% chance of success, while a 60-day project has only 29% chance of success, all other things being constant. In addition, projects that succeed do so by small margin. 25% of projects found at only 3% or less over their goal. 50% raise 10% more than their goal. As we can see, goal and duration are crucial to the success of a Kickstarter project. So in our project, we want to give some insights on how to set a realistic goal and set the deadline cleverly. We do so by building a machine learning model using RNN and SVM to predict whether a Kickstarter project can be funded successfully given necessary information. Here are the features and labels we consider in our model. We have more than 320,000 valid data in our dataset. The first feature is the name of the project, and then the category it belongs to among 13 main categories, the currency, which is one of the 14 currencies, duration time, which we calculated from launch time and deadline, and the goal of the funding converted US dollars. If the state of the project is successful, we label it 1. If the state is failed, we label it 0. We discard all other states, such as cancelled and live. Here are the distributions of the projects with respect to categories and currencies. Before we feed the data into our model, we need to do some pre-processing. First, we transform categorical data into matrix of integers. To do this, we use the label encoder and one-hot encoder functions in sklearn. We use the first one to transform strings into numerical data, and then the second one to get an array of the one-hot representation of the data. Each row contains all zeros except for one position, which corresponds to the category of this data. For example, in the currency feature, CAD will be encoded into 0, 1, and zeros afterwards. We pre-process the data in main category and currency. Second, we would like to extract the useful words in the name feature and generate a vector for each word. We first remove the stop words, punctuations, and numerics in the names and stamp text to get the useful roots of each word. Here are some of the tokens after the pre-processing. Then we generate a vocabulary of the 1,000 most frequent words. We convert each name into a list of integers between 0 and 1,000. 1 to 1,000 for the corresponding word in the list, and 0 for the words not in the 1,000 most frequent words. After generating the one-hot vector for words for training and testing data, we would like to put them into the RNN model. However, we failed at our first approach. We re-examine our model, which would be described in the next section, and realized that it is a characteristic of the package we're using that we can only pass vectors of the same length into the model. We did some literature review and found out that a feasible solution is to pad zeros at the end of shorter sentences. Therefore, we found out the maximum length of the training data and testing data and pad zeros to make all sentences the same length before training our model with them. Here's an example of the name after padding zeros. Then we constructed our RNN model to check if we can predict whether the project will succeed using the name of the project. We label it 1 for success and 0 for failure as before. We use carrots for our model construction, as in the homeworks we did before. We have a sequential model with the embedding layer at the front, followed by a dropout layer. Then we have a simple RNN layer, which gives the final prediction result. The embedding layer is mapping a vector with integer values to a matrix, in which the vectors represent the spatial location of words in an x-dimensional space. Here, x is a hyperparameter which we set to be 128. From this perspective, we are able to measure the Euclidean distance between words, and the distances are shorter if they're closer in meaning. Here's an example of the embedding if we project it to 2D plane. All countries are on the left and capitals on the right. The simple RNN layer is an RNN layer which has a many-to-one structure. We set the dropout rate to be 0.2, both in the linear transformation of inputs and the recurrent state. And regularization constant lambda was set to be 0.01. With the setup of model and hyperparameters, we achieved an accuracy of around 60% on training and testing data. Here's the code and the result. With this result in hand, we proceed to our SVM model. We trained our SVM model both with and without the predicted labels from RNN because we're not sure whether it would improve the performance of our prediction. We used the RBF kernel, we used a 5-fold cross-validation, and found that the best hyperparameter to be gamma equals 0.001 and c equals 5. Here are the results of our SVM model. Without the name feature, we got a test error of 0.2. After adding the results from RNN to the features, the test error decreases to 0.17. We conclude that adding the name feature slightly improves the performance of the SVM model. With a test error of 0.17, we believe it is reasonable to refer to this model when starting a Kickstarter project and to predict whether it will be successfully funded with a proposed name, goal, and duration. It is surprising that with very limited features, we can reach an acceptable results of prediction. In the future, we may try using more attributes of the data in the SVM and more complex RNN structure to see if we can get better prediction performance. One possible defect of this model is that we are using a very small vocabulary of only 1,000 words. Later, we may try to generate a larger vocabulary list and thus more dimensions in name vectorization, hoping to capture more information from the names to get a better prediction. That's all for our final project. Thank you for watching.